curious about is can it film videos? Nope. Not a curious about. That's sweet. How was that? So, all right. So I made a thing here, and it worked, and that's really rare. So celebrate that with me. Come on, dude. Sorry, I should have reset it after that. This thing here. There we go. All right. So maybe I can just all right. So that's a lot of these. Alright. So I'm going to displace this 100, displace this 20 centimeters, and I want you to check it out. Alright, so over on the pear deck, what do you notice? Oh. Just save the video with one that I don't know. Could be exactly. Alright, so our friends notice things like, as time goes on, the displacement becomes less. It bounces back and forth, but less bounce each full pass. It oscillates. Ooh, good word. Cart moves in both the positive and negative direction. Velocity continuously decreases. Distance in each direction continuously decreases. Cart reaches velocity of 0. Cart's moving back and forth, gradually slows and stops. Moving back and forth, getting slower. Ooh, some energy is transferred to friction is the reason it's slowing down. What do we call that transfer of energy by friction? That's dissipation. Pickies out, my friends. All right. The two springs make the cart oscillates. All right, cool. So you mentioned some things that were changing. Is there anything not changing? Let me run that by you. New question. So dig it. Ready? Anything not changing or somewhat constant about this? All right, so let's check this out. Time it takes for each oscillation. Spring constant of each spring. Constants in the spring, which is springs stay the same. FSP and FG are constant. Time it takes for the car to change direction. So a couple people are mentioning time. What do you think about that claim? Let's check it out here. Okay, so here's kind of the, I should probably ask you about this position. That must be true of this position. Okay, but from this position, I'm going to slide it 10 centimeters over. and kind of like look and listen. Okay? If I slide it 20 centimeters over, kind of look and listen. If I go 30 centimeters over, what do you think? Time? Okay. So even as this thing decays down to a velocity of 0, as friction dissipates energy here, the time it's taking to get back and forth is kind of steady. Keeps a pretty steady beat here. This is how they built the first metronomes. They used to string a small woodland creature up between two springs suspended from trees, and then it would swing back and forth. That's how they kind of drum majors. So even as this thing decays down, that time is pretty steady. So that time specifically, we call it the period of oscillation, the time for it to go back and forth. So period is from here till it returns to that position. Okay, when we're talking about period, it's the time to return to that same position. Okay? What can you tell me about this position here in the middle right now? Let's ask you that question. What do you know about the object at that location? Well, you're kind of answering like right now, but in general, it's at equilibrium. All the forces cancel out, or we would use the word balance. Forces are balanced at this position. Yeah. Okay. So let me try this one on you for size. Okay, the force is balanced at this point. I'm going to throw a true/false your way. Okay. So I measured the spring constant K earlier, so that I know that the cart is presently experiencing 10 newtons of force to this would be the positive direction, right? 10 newtons in the positive direction and 10 newtons in the negative direction. Those forces are equal size and opposite direction. Therefore, they constitute a Newton's third law force pair. True or false? So said again, this cart is experiencing 10 newtons in the positive direction, 10 newtons of force in the negative direction. Those forces are equal in size, opposite direction. Therefore, they are a Newton's third law force pair. And that's where we're at with that, so you better have a talk with your neighbor there. Set them straight.
I'm pretty sure it's along where if you put the feeler and dealer around, you're the same person, right? So we're talking about how the cart is the same force in the spring 14
All right, you talk to your neighbor about it. Go ahead and revote while I have that up on the screen. So okay. So now nobody thinks that's the case. Now one person thinks that's the case. Now nobody thinks it's the case. Damn it. All right. Now nobody thinks that's the case. So why not? Okay, short answer would be that, bro. Why are those two equal size, oppositely directed forces not a force pair?
Still locked.
It's still locked?
Yeah.
That's cool. There you go.
You people type fast.
Gentlemen, where did the video that I shared to OneNote go?
Oops. All right, what are our friends saying on the internet now? Force pairs are when it's the same type of force interacting on the object. Springs are two different forces acting on the cart. I mean, they're both spring forces, friend. Force pair would be if the amount of force the cart feels from one of the springs is the same as the spring feels from the cart. Same type of force, but different force. Okay. Force pairs are not opposite. Feelers and dealers are different, not just swap. Force pairs have to be between two objects. The springs are interacting with the cart, not each other. Feeler dealers aren't opposite because they are forces between the cart and two different springs. Force pairs between the same two objects. Okay. It would be the force experienced by the cart from the spring and the force exerted on the spring by the cart. The two springs are two separate forces. So another way of thinking about this too is that force pair thing, that's an always state. Okay? And as soon as I do this, now how does the force the cart feels in this direction compared to the force the cart feels in this direction? Yeah, they're different. Okay? And I can't do anything to make that happen to a force pair. So that's enough. They just happen to be equal size and opposite directed in the middle because this is the equilibrium position. Okay? So that's a situational thing. The forces are the same size. Riddle me this, Batman. We've already identified the time as being kind of constant here. So my question to you is this: what could we alter here that would result in the time changing? I've already shown you that the displacement doesn't change the time. But what could we do that would change the time here? So you can come up with a thing or two with yourself. Ooh, that's a good one. What are our smart friends saying on the internet now? Mass of the cart, length of the track, friction, slope of the ramp, mass of the cart, springs, lower spring constant, add mass of the cart while it's still moving. Change the mass of the object, incline the track, angle of the ramp, with the cart. Cool. I had not seen angle of the ramp come up yet today, so I'm excited to try that. Let's see what happens over here. Cool suggestion. Okay. Did it seem to affect the time? Oh, interesting. So we'll have to look into that sometime. Other suggestions. Mass of the product. Let's look at that. Go big or go home, right, bro? George. or you take a video of where there's an incline, how the incline would feel about it. Okay. Instead of the incline. So can you do 7 things at once? Well, yes, kids, but not 8. So grand speed can displace the 5 seconds. Slightly? Jeez. Cool. What I really like about that video is Grayson is really disinterested. That's still not good. All right. So we did mass. Ooh. So yeah. So like increasing the mass. Like clearly, what happens here? Does that do anything? Bigger mass, slower. So what happens to the period? The time to go all the way to and fro. Okay, increasing mass, increasing the period. All right. And then the other request was to change the common request is to change the spring constant. So I can do that real quick. We'll fix the relative term. There we go. All right. So these have a spring constant which is roughly 20 times greater than the other one. Okay? What do you think? Bigger spring constant, what happened to the period? Smaller, less time to go back and forth. So increasing the constant decreases the period. Increasing the mass increases the period. Okay? I can now release to you a slightly less redacted version of the equation sheet. Okay? Where is it? Over here. Okay, and the AP equation sheet will reveal what's hiding behind those marks. Let me see if I can just pull this out and over. So you might add this in on your equation sheet if you have a copy. But you'll get one on the day. Okay, so I should jot down what we noticed here. Things we noticed: increasing mass of oscillator increases period, increasing spring constant for oscillator decreases period. Okay. Changing angle of incline did not change period. And changing displacement from equilibrium did not change period. We got these equation-y things. Okay. I'm going to try to post those videos somehow, some way. Share. Let's see how long that takes to upload. So then I want to consider a few other things as well. Let's talk about. Let's see. Remote. Oh, what did I do to myself? Ha. Skip this. Sorry, I'm trying to be real lazy here, real quick. Yeah. And that's not how that works. I want to introduce you the concept of amplitude. There we go. And amplitude, oh, come on, is sort of referring to the maximum displacement from equilibrium. So we'll just kind of zero things out at equilibrium, okay? So this is the equilibrium position. X is 0, and then the X max would be positive A, and the X min would be at negative A. So then I want you to think about some of these other things with your neighbor a little bit there. When is the force in the positive direction, or where is the force in the positive direction at a maximum? Okay, so have a think about that quick, and you can slap that into the Pear Deck here. So again, what I'm asking you, where is the force at its greatest positive value? Does not need to be in paragraph form. So I'm listing out some positions for you here. X is negative A, X is 0, X is positive A. Those don't look symmetrical, Mr. Harding. That looks better, Mr. Harding. Okay. You're having to think about that. Let me see if I can get at these videos. Nope. All right. What are our friends saying on the internet? The card's at the X min position. Card's at its farthest negative position. In the middle at negative A at position 0, X equals 0. So we're kind of split on this question of when is the force the most positive. Okay, so kind of we're talking about like the FU, if you will. When is it the greatest positive value? And we seem to be pretty split between 0 and negative 8. So please have a ponder with your neighbor there for a second. I'm talking FU here. Talk to your neighbor.
negative A, then the string is going to be belongs to that. So it's the magnet pointing at 0, where it's going to be shorter relatively. Its velocity is smaller over here, but its acceleration is bigger in this direction.
All right, so you're hopefully revising your answers on Pear Deck after you've talked to your neighbor. And let's see what our friends are saying now. Farthest negative position, x equals negative a at the min, x equals negative a, negative a, negative a, and then a bunch of redacted responses there. But yeah, that's kind of what's happening here. Okay, when you take it to the farthest left position, your force is going to be at its most positive. Okay, when you're at that spot, you're going to have an F that points that way, or an FU at least, we should say. Okay, so that's negative A. What about low-hanging fruit here? What about when is FU at its most negative value? There are friends. I gotta get rid of some of these extra things. There we go. Boop. Positive A, positive A, positive A, positive A, positive A, A. All right, so you got it, right? So now when it's over at positive A, the force is going to be back towards x equals 0, back towards equilibrium position. So this type of thing is called simple harmonic motion, or SHM, and it's typified by an object that experiences a linear restoring force. It's called a restoring force because it's trying to take it back to the equilibrium position, okay? And it's linear because Hooke's law says that the force is the opposite of kx. So doubling the stretch doubles the force, tripling the stretch triples the force. But that's kind of a characteristic of simple harmonic motion, a linear restoring force. This is kind of redundant, but directed towards equilibrium. All right. So FU in the negative direction, positive A. When is FU 0 then? We don't need to pair deck that, right? At x equals 0. All right, different question. Let's talk about acceleration. When is the acceleration, or where is the acceleration at its most positive value? Run that by yourself. Throw it in the pair deck, and then I'll give you a chance to talk to your neighbor about it after that. All right, our friends are saying negative A at either end of the track. 0, 0, 0, middle of the path, back from a stretch. Lots of variation there. So talk to your neighbor about that. When is the acceleration at its most positive? Come on, I'm trying to make you look smart on the screencast here. All right, let's see what our friends say now. Negative a, negative a, negative a, negative a, x equals negative a. Yeah. Negative a. Why? Because FU is the greatest, and that's where acceleration is going to be the greatest because there's that whole relationship there, right? FU equals MA. Mass is not changing. So where the unbalanced force is at a max, that's where a positive max, that's where your acceleration is going to be at a positive max. So that's negative a, so that's positive a. So how about this question then, friends? Where is the acceleration going to be 0? Where is the acceleration going to be 0? And how are we doing with that? 0, 0, A, 0, 0, 0, 0, 0, 0, 0, deleted response. Okay? Forces are balanced at that instant. There's no unbalanced force. And if there's no unbalanced force, there's no acceleration. So this occurs at x equals 0. All right. Be kind of specific in your answer to this one. But where is the velocity at the most positive? Okay, so it's not really just a position, but there's also some context maybe. The velocity will be most positive when what is true? Our friends on the internet are saying 0 from negative a. X equals 0 coming from negative a. 0 right before it starts to slow down. 0 moving from negative a to a. So yeah, you got the idea. So it's got to be when it's coming back from negative a because it's had a period of positive acceleration that whole time. So x equals 0 from negative a. X equals 0 from positive a. Okay. Last one, not true. But last-ish one, when is velocity 0 for that object? Or where is velocity 0 for that object? Now you're cooking with fire. A or negative A, positive A, negative A. Either end of the track where oppositely signed acceleration makes the velocity go to 0. All right, because you're picking up on that because when it's got a positive velocity, it's got a negative acceleration. Well, that's not true. Not the whole time, but all right. Okay, so then we take it into like the energy realm here a little bit. When is the elastic injury going to be at a maximum? Maximum elastic energy. The College Board equation sheet, by the way, symbolizes elastic energy with us, because that's reasonable. Quick answer from everybody. Let's see what you said. Oh, I didn't do it. That doesn't help. There we go. That's the same answer, though, yeah. So it kind of looked like you'd already put it in. A or negative A, yeah. Okay. So that's where the stretch of the spring is going to be the greatest. So A or negative A. Where is it 0? Oh, you knew that already. X equals 0. EK, where is EK going to be at a maximum? EK at a maximum. 0, 0, 0, when Vmax 0, 0, 0. So pretty universal there that maximum velocity and maximum EK occur at x equals 0. So yeah, things to note there, that both of those energy quantities go with the square of the position or the square of the velocity. So it doesn't matter negative or positive A, you're going to have the maximum EE. Negative or positive velocity, you're going to have the max EK at x equals 0. EG, that's not really on here, but that's what's shaken. What are the other things we need to mention here? They're escaping me at the moment, but that's kind of how that goes. So note the things that go together. Unbalanced force and acceleration, those are in sync with each other. They're at the maximum at the same point. They're at 0 at the same point. Same is true for the EE. That's going with those things. EE is at a maximum where the acceleration, the FU are at a maximum. EK is going with velocity. It is possible, and in fact, it is happening, that your velocity is at its greatest when acceleration is 0. You can have velocity with 0 acceleration. Your acceleration is greatest where your velocity is 0. You can have acceleration but have a velocity of 0. Those things are all possible. All right. So we're going to take this back over to the lab. We're already at 37. Yeah, I'm all screwed up on the clock. All right. So catch a mix. Got that hot spit and fizzy breath here. Come on over to the lab, friend. So it's another kind of similar idea. Now this is homemade. That hook is just screwed into a stopper and held in place by friction. So I would not get in the plane with this thing. I'll give you sports. But I'm going to pull this thing back. Pull it up like chin, chin, chin. I'm going to let go of it. Okay. Not brave, but yeah. What's kind of going on here? So take a moment with your neighbor and kind of talk about similarities between this and string mass oscillation. Should have done with this. Okay. So, riddle me that, Batman. What are the similarities here to the other one? Oscillate. Is that true? So run this by your neighbor really quick. This point down here where the velocity is 0 is the accelerating. Sorry, that's the velocity is 0. At this point where velocity is maximum, is the acceleration 0. Where I missed. Why or why not? Run that by your neighbor. Oh, yeah. Yeah. All right, did you fall for that? Did you get it fixed? What will be true of the free-body diagram down there? Is it equilibrium? No, it's what? Scooped up, right? Yeah. Why? Because the surface. Okay, so think about that. How does tension compare to gravity when it's at that low point? Tension's got to be greater than gravity. Okay, it's a circular motion. Where's the EK greatest? Bottom. Through the EK on the ends. Lowest. Zero. Yeah. How is the injury? How is the potential for injury stored out there? Gravitational. So on the energy graph here, we're working back and forth from high EG at the end, no EK. To the point in the middle where the EG is at a minimum, the EK is at a maximum. Okay. We'll do a little more work with this to kind of better understand the factors that do affect pendulum and that don't affect pendulum. That's all kind of tied into the SHM intro activity that I have for you to check out on master. So if you want to, you got 7 minutes left, or go and hop on the master and get it built back. That's not loud or any question. That's my goal. I want to
I go down one. No, 3 questions, but they're all my Hey guys. Even running
How do you make the choice?
what? This is the best choice.
Sorry, I hope so. They know.